This is Unit 1E. It deals with microwave and infrared uses. So starting at the bottom we have energy, and as we're now familiar with, we have got electromagnetic waves which transfer energy from place to place. And as I've already said, we're interested in infrared and microwave. Now the first place to start is to think about cooking. Now both of these waves are used in cooking. More traditionally we use infrared, so if we think of a heat element or a barbecue, and this will send infrared waves, but it will only hit the surface, it won't go any deeper, and from then on we're reliant on conduction to heat the middle of the food. Now microwave ovens have been around since about the 1970s, became popular in the 1980s, and the reason they're popular is they're much quicker, and they're much quicker because the microwave can penetrate into the middle of the food, and the biggest effect it has is on water molecules. So a lot of food has water in it. In fact, manufacturers make sure there's a lot of water there, and the microwave is absorbed by those molecules. Now microwaves are also used, as we've seen in previous presentations, in mobile phones. Now there may or may not be a risk there, and there's an ongoing discussion about this. So far we haven't found any really convincing evidence that it's dangerous, but it's still early days. In 30-40 years time we might find there are serious health problems. So here we've got an image that compares the person's head before and after mobile phone use. So a couple of strategies that people are adopting is to minimize use, or keep it away from your brain, or use hands-free sets. Now we also have problems with transmission occasionally. We've all experienced this. Now why is that? Well, it's very simple. Things like the curvature of the earth or a mountain or a building get in the way. Now coming back to infrared here, in terms of its emission, absorption and reflection, we need to have a quick think about the effect of colour. Now here we've got four situations. We've got in each case the same amount of infrared radiation arriving from the bottom, and we can see what happens. So if it hits a reflective white surface, a lot of it is going to be reflected. There's always a bit that's absorbed that will conduct through, but again here on the white side, the white is a poor emitter. Now emission is the thing that people struggle with more, reflection is more obvious. If we think of a black surface, we're going to get a lot more absorption. Again, it will conduct through. But if we've got a white surface there, the emission will be, the overall transmission will be less. So if we've got a white surface, we're going to get strong reflection here, a little bit of absorption, but we're going to get strong emission from this black top surface here. So the best situation, if you want the heat to go through your surface, is to have black on both sides. So lots of absorption and lots of emission there, very strong emission, and that's in contrast to the white. So insulation often has a reflective surface facing the heat source, but also a reflective surface on the far side. And we can see that here in our thermos flask. This is on the outside obviously, and it's shiny, so it's white and, well, a light color, so it's a very poor emitter. So we can see here in normal color two surfaces, white and black, and here we can see it in infrared, so we can see this is dark in infrared, which means not much emission. By contrast, sometimes, such as in the back of a fridge, we want there to be lots of emission. We want to get rid of that heat, so we're going to take a dark color, which we can see in infrared is actually very bright, is transmitting lots and lots of waves, which we can see there. So there we have it, microwave and infrared uses. We've got a contrast in cooking in terms of how deep the waves go, and then we've got our look at emission in particular, and that shiny surfaces are poor emitters, black surfaces are good emitters, and we will use them accordingly.